Okay, for the remaining of the class today, I'd like to go through another, I guess, important milestone in the kind of deep learning stuff, which is convolutional neural network, so it's called CNN. So CNN is pretty famous for do image classification, right? But again, we just did image classification using the artificial neural network, right? ANN, right? So what's wrong with it? Right, so why do we need to use CNN, right? So people realized very quickly, after the success of ANN to do image classification that it doesn't scale. If you are going to do 28 by 28 image, maybe that's okay. But nowadays the image are, I don't know, like 4,000 pixel by 4,000 pixel, right? From your camera. That doesn't scale. Like it's gonna take way too long to do ANN because it's too overkill. So that's why people come up with convolution, and that saves a lot, huge computational power, and that make it possible for you to, like for your phone, to classify cat image on your phone using, like whatever processor in your cell phone. Without convolution, doesn't work. Okay, so that is a huge computational efficiency that's gained using convolution. Okay, so let's explore this thing a little bit, right? So first, you have to understand what the convolution is. Okay, so this, bear with me, a little bit of math, but not too much. Okay, so the convolution is in operation. This thing right here, star. Okay, so when I want to convolute between two things, and two things in here, it's just a vector, sequence of number. But later on, we're gonna expand this into a matrix. Okay, but right now, just think about it as a vector. I want y, so my y is the result of the convolution operation between two vectors x and w, okay? And these are the operations. It's just a summation of multiplication between the elements of x and w, although there is the shifting of the elements happening, okay? So I want to show you a little bit more visually, all right? So for example, if I were to, I want to calculate y, right, at the position of 0. So y0, right? So y0 it means that my I, so the index right here is equal to 0, actually this one, right? I want to calculate y at I equal to 0. What do I have to do, right? So for an infinite array, so that means that x and w is a really, really long vector. Then these are the operation. I have to do the infinite sum, right, of the multiplication between x at the negative k and k. So that means that if k equal to 0, that means I have x0 and w0. I have this pair. If k is equal to I guess 1, right, I have w1, but then my x is x to the negative 1. If my k is equal to negative 1, I have w of negative 1 and x of 1. So as you can see that it's just a way to kind of make sure that we have all the contribution from the two vectors, right? But it's just shifting the location where you do the pair multiplication, okay? Let's look into another example. If I were to have, I want y at index I equal to 1. So that means that I have to do a little bit of shifting, meaning that if I were to fix my x in the same place, right, you can see that this is the green column, like my x the same, right? And the operation is that I move w, shift it to the right. As you can see that w1 gets shifted to the right, right? w0 to the right and negative 1. Right, so that's the operation in order to get y of position 1, okay? And again, if I want y at position negative 1, all I need to do is just doing the same thing, but with the w shifted to the left, like that. Okay, so that's called the convolution, okay? So each convolution consists of a bunch of multiplication with pairs, different pairs of from the two vectors, and then summation with one another, okay? Okay, so we don't have, in our problem, we don't have infinite array, we have finite array. So when you have finite array, then things get a little bit more complicated because now my summation is no longer an infinite sum. So my sum is only as much. So let's say that x is something that is large and w is a smaller vector, right? And then we call w kernel later on. Okay, so w is something small. So w has a smaller size of m. Okay, so m is the size of the w array. Okay, so when we do the summation, we only do the summation up to m minus 1 because that's the size of the w array or the kernel. Okay, and the equation is a little bit more complicated, but I just want you to visualize it as sliding of the vector. Okay, for example, if I have vector x that has 6 elements, x0 to x5, and my kernel w is only 4 elements, so w0 to w3, right? So my m is equal to 4, my n is equal to 6, so that's the number of the x, right? So my y at different position is going to be equal to this summation, which only from 0 to 3, so that as many as the number of elements in w array. Okay. Okay, so it might seem complicated, but actually if you think about it as a sliding window, it's actually not that difficult. Okay, so again, if I want y at position 0, so y0, right, I gotta do this summation. And this summation comes from, the first is that I need to match w at this position with x, right? And I do the cross multiplication where w0 go to x3. Okay, let's see like this. This gone here. So w0 go to x3, w1 go to x2. That's this term over here. w2 multiply with x1. That's this one right here. And w3 multiply with x0. You can see that it does have a little bit of the crossing, right? And then you do summation with one another. If I want my y at position 1, which means that I equal to 1. What I do is I shift w to the right, and I do the same cross multiplication and then summation. So w0 multiply with x4, right? w1 with x3, w2 with x2, and then w3 with x1, like that, right? And then do the summation to get y at position 1. And again, if I were to do I equal to 2, which is y at position 2, and I do the cross multiplication like that again, right, to get all of this. And then again, I think I made mistakes here. This is supposed to be 1, 0, 1, and 2. Sorry. So again, my y, my resulting y, like from this operation, it's going to be, my y will have the length of 3 elements, right? As you can see here, my w cannot slice any further because it's the n, right? So there is, that's something that you can see that might be a little bit confusing in terms of, you know, like why do we need to do this like crossing like this, right? So why can't we just do something more straightforward, like matching things on the same position? And that's exactly why we are reversing the filter so that we don't have to do just that, okay? So the original way of doing the convolution is to do it this way. It's going to be the cross multiplication. But then the way that we are going to do it in our machine learning model is actually we're going to reverse the order of my W matrix or the kernel such that when I do the multiplication, the index actually, like the location actually matches like this, which is easier to do the coding. We don't have to do like this weird cross multiplication. So that helps with the coding, like the complexity of your code, right? So essentially, you are reversing the kernel. That's how we do it numerically in machine learning, okay? So that it become, you know, instead of W2 to W3, it become 3 back to 0, something like that. Okay? Another thing that we can do is that, as you can recall, that if you were to slide W along with X, then, you know, your choice of Y, like the number of elements in Y matrix, vector, is going to be limited to whatever the size of this, right? So we need more flexibility than that. So what we can do is called the technique called padding, okay? So If we don't do padding at all, as you can see that if you want y at position 0, you're going to have to do the convolution with this too, right? And when you move w to here, right, you slide one step, then you have another position here. And then w can also slide to this position in order to end up with y at position 2. So if you don't do any padding, meaning that the original way, your y is going to end up with just 3 elements, which is kind of not too convenient, because now your y is actually smaller than x. So this is different size. So that's something that we want to fix, and we want some more flexibility. Okay. So now what I can do is that I can pad my x with a 0. Okay. And if my x is larger, that means that I have more space for my w to slide left and right. That means that each slide will give me my y value. And that means that if I were to do padding equal to 1, that means that I do 1 from each side, I get y to be like now 5 blocks, which is nice, right? I can control the number, the size of my output vector, which is y, to be 5 and 3, depending on my padding value. Okay? If I were to do padding of 2, that means that I put the 2 0 on each side of the x vector, and that means that my w has even more place to slide, and that means that my output vector, which is y, will have even larger size. Okay? So essentially the padding will allow me to get the size of the output according to what I want exactly, essentially. Okay? So now you are aware of the technique called padding. You're aware of the technique called reversing the filter, just to make things easier to compute, right? Okay, now we are, and again, a different type of padding is available when we're doing all of this convolution. Okay? So the first is called full padding. Okay? Full padding means that you are going to have a lot of padding so that your output is actually larger than your input, right? Your output is y, your input is x, okay? So if you do full padding, you're outputting something that is larger than your input, okay? If you want to do same padding, so that means that you want your output and input to have equal dimension. This is something that we want always commonly used in our CNN application, because that makes things easier in our code when you have the same output and input dimension. So that's something we want. And if you want something that is smaller in terms of output comparing with the input, then it's called valid. Okay, so p equal to 0. It's called reduced dimension. Okay, so again, these are the names that we're going to use when we're actually constructing the layers in our CNN model. Okay, the example of all of these are listed below, where if you do the full padding, that means that you are going to have the output that are larger than the input. So right here, it shows that you have 5 elements in your input. If you're padding, with two blocks on the left and right, that means that you are going to have a larger output than your input. So the green is larger than blue. Okay? But if you choose your padding with just 1 block on each side, and your kernel is 3 blocks, then that means that your output is the same as your input, which is 5 blocks. So this is the one that we use quite regularly. And if you don't have any padding at all, that means that your output is going to be smaller than your input. As you can see that green only have 3 blocks and blue have 5 blocks. Okay, so depending on what you want, you can kind of control the dimension of your output accordingly. Okay. And the next concept that we need to know is called stride. So stride meaning that when you slide your W vector or kernel, you are going to slide depending on how many steps you want to slide, like how many skip are you going to have. If you have stride, which is s equal to 1, that means that you don't skip any blocks at all. You slide in order of your blocks, basically, right? But comparing to something that calls stride number 2, like s equal to 2, that means that if you want to slide W, you actually skip 1 block. And the stride also control, the dimension of the output too. Okay, so right now you have stride and you have padding that can control the dimension of your output. Okay, and in the end, you have lots of options, but you can kind of calculate what's the output from your input, according to the size of your input. Okay, according to what padding you have, according to your filter size or size of your W, and according to your stride. Okay, so that will give you different output size. Okay, and this is the equation that you can use to calculate. Okay, so it just like you can work it out algebraically too, but you just be aware that this thing exists. That's enough. Okay, so let me just show you real quick how this thing comes about, right? So let's use the first example to see what the output's gonna be. Okay, so my output is gonna be equal to the floor, like the floor meaning that takes the I guess the lower integer of the results, right? So n equal to 10, so that means my x has 10 blocks, so 10 right here. Okay, plus 2p, so p is the padding, so 2 times 2 is 4. Okay, subtracted by m, which is the size of my kernel. Okay, w. Okay, and divided by the stride. Okay, so that's going to be equal, m equal to 5. Okay, okay, which that's kind of weird. I should get 10, right? Do I get 10? I don't get 10. That's weird. N 2p, which is 4, subtract by m. Oh, I forgot plus 1. That's why. Okay, yeah. If you work this one out, it goes into 10. I forgot the plus 1. Okay, so something like that. So if your input is 10 and your output is 10, so that means that it's called same padding. That's the name that we always used. Okay, a little bit of jargon. Just kind of, I don't want to confuse you too much, but I gotta mention this one. So again, if you do convolution means that you are going to use the cross multiplication. So that's the reason for this negative sign right here. Okay, but if you were to do something that we are using in the machine learning, which is the reverse of the filter, what you are actually using is called cross correlation. Okay, so that's a term that we use in mathematics or physics. That's called convolution and cross correlation. Okay, and the difference between these two is essentially just the sign of your of this term right here. So either you want to do the cross multiplication or not. That's all. Okay, so in the deep learning jargon, we are using cross correlation because we don't want to be doing cross multiplication because we don't want to keep track of things that are here and the other one on the other side. That's kind of hard to do the coding. We want to switch things up so that the position kind of lines up. So it helps us with coding. But then I don't know why we actually using cross correlation, but people in machine learning field always refer to this operation as convolution. So it's something that has been around for a while. And it's quite confusing because like signal processing people always say that, you guys are doing cross correlation, but then in the machine learning paper, we always refer to this operation as convolution. Okay, so so this slide just shows you that some of the jargon get mixed up in different fields, and sometimes it's quite confusing for the newcomer. If you come from the signal processing, what we are using as the convolution is actually called cross correlation. Okay, so what I was telling you previously applied to the vector, right? But then in our image processing world, we don't do vector, we do matrix because in image it's always 2D. So instead of just one-dimensional convolution, we want to do two-dimensional convolution. And the only difference is that now, instead of summing only in one dimension, we are doing summation in two directions. As you can see that everything has two dimensions. The algorithm is pretty much the same in each dimension. It's just that the summation is more involved because it has multiple dimensions. That's all. okay? And the way that we visualize convolution in 2 dimension is actually the same as in vector, but now we have like a matrix, or you can think of it as an image, okay? So think about this. We have the input image. This is the image, like a cat picture, for example. And we want to do the convolution of that with the kernel. This is the kernel. This is something that we're actually learning in our model. Like this, the model will supply the kernel for us to do the convolution. And when we do the convolution, what we are doing is that the kernel kind of scan through the image. And each of the scan will be the multiplication of this and that, right? So the position of the multiplication between the kernel and the input image exactly lines up like this. So this point go through this point, and then they do the multiplication with each point like that. And then everything got summed into just 1 pixel in the output image. Okay? So as you can imagine that, each of the scan, produce, each of the pixel in the output per se. That's how we do the convolution in the image processing. Okay? Okay, you'll see more examples in this. Okay? So just to be clear, let me work out some of the example that might come up. Okay? So suppose that we have an image that looks like this. This is a very, very small image. Right? And suppose we want to do a convolution with respect to this kernel. Okay? First of all, what you want to do is actually like the image, the input image will have the dimension of 3 by 3, right? This is 3 and this is 3. So that is it's specified right here. So 3 by 3 image, so 9 pixel, okay? And also you have the kernel. This is the kernel, which is 3 by 3. So that is this number right here. So M is 3 by 3, okay? And since if you don't do the padding at all, that means that you are going to end up with just 1 pixel as the output. So that's too small. So we want to do a little bit of padding. So padding is 1 and 1. That means that we are padding 1, 0 on each side along the x direction. So that's p equal to 1. That's the first one. Okay. The second number 1 right here is actually padding along the y direction. So in the end, you have the image that is slightly larger through the padding, although we just use the value 0 in the padding region. Okay? And next step, we are going to do the convolution with respect to the kernel, right? So these are the input with the padding, okay? And first, we want to line up the W, okay? Although with this kernel, we want to reverse the kernel, so WR, so that's something we reverse. The reason that we reverse this is that we don't have to do the cross multiplication. So we are using this kernel to lines up with the image, okay? And if you can imagine, this is where the location of the kernel is going to be. So this is W of R at the first, the first scan, okay? And what you are going to do is that you are going to do the multiplication of that. So you are going to do 0.5 multiplied by 0, 1 multiplied by 0, like that, 0.5 multiplied by 0, right? And so on with the second step. So 0.1 multiplied by 0, 0.4 by 2, 0.3 by 1. And then so on, 0.4 by 0, 0.7 by 5, and then 5 by 0. Okay, if I were to write this one out, okay, this one is get too clutter, but I'm just pick the one that is non-zero. So essentially, this cells right here got multiplied with this cell. So that's the one that is non-zero, right? So let me work it out. So it's going to be 2 times 0.4 plus 1 times 0.3. Right, plus 5 times 0.7 plus, this one is zeros again, so I don't need it. So it's going to be this 3 terms, so that would be 0.8 plus 0.3 plus 3.5, so that end up with 4.6. So that is the first pixel in my output image. That's the result of one scan, right? And the next scan is I'm going to move my W to the left or to the left or below, right? But since my stride, my stride is 2, that means that when I move my W to the right, I need to skip one row. I need to skip one block. So that means that my second scan ends up at this position due to the stride equal to 2. If my stride equal to 1, then I cannot skip the block. This one I skip one block, go to the right, and I perform another convolution with the original image. It's going to be along this block. So I do the multiplication and the summation in order to get 1.6. That value is the output image, okay? And then I do another stride to the y direction. I need to skip one block, so it's going to be down here. So this kernel is going to be convolute with this region right here. And I do the multiplication and then the summation in order to get this value. And then I do another slide to the left, and I need to skip one block because of the stride equal to 2. So this kernel comes down here, which is going to get multiplied to the block here in my input image. And then it's going to get this value 7.5. Okay, so that's how the convolution works in order to go from this input image to another output image. That's the thing that's the kind of the crucial process that gets done in the CNN. Okay, so all of this is actually just a bunch of operations, but we're going to use all of this to construct the CNN. So CNN is convolutional neural network. Okay. Let me see the time. I want to make sure that. Okay, so we do have some time. All right. So to start with CNN, it's something that quite closely related to how we see things. Okay. So visual recognition. Okay. So we can see this picture and we say that this is dog. Effortlessly, right? How do we do this? Right? We don't know how the brain works at all, right? But people have been trying to figure out how our brain works, called the visual cortex, and use this kind of logical thinking or logical way that we process image, and then kind of construct the the numerical function like CNN, basically. Okay, so how can we construct a computer model that actually recognizes visual objects, right? So that's the reason people come up with convolutional. That's the motivation for the convolutional neural network. Okay, so the architecture, the original architecture of CNN emerged from study of brain visual cortex. Okay, and in the visual cortex, something that's quite important is called local receptive field. Okay, so this word is a key word, local. So it's almost like this. When we see things, we don't see things globally. Like we don't see the whole image at once. When we see image, we see edges. We see kind of like little blob of things. And then we kind of construct things into the representation of something that we can relate. It's called local receptive field. So that's a keyword that makes it very, very different from ANN. When we do artificial neural network, we actually linked everything together. If you input an image into ANN, what it's doing is try to make connection from one pixel to the rest of the pixel. But that is not how we see things. When we see things locally. And then we kind of sum things up into a more local region. Combination of each region goes into features. So that's kind of the motivation why we're doing something like convolution, because convolution is a local operation. It's not global. Okay, so that's the thing. So when we see things, we only see limited region. That's another keyword. Okay, and from this limited region, it gives us the ability to detect two patterns, like edges, like curve like things that are blacks and white and things like that. It's like pattern come from seeing things in the limited region in a lower level pattern too, okay? So we don't see the dog at once. We see edges, we see blob of black things, like we see like things that looks like this, and then we kind of combine it together into a more like higher order level representation, like dog, which has 2 eyes, 1 nose, and a tongue, something like that, okay? Another way that you can visualize things is like this. Like when we see this picture, we see edges, kind of like a lower level shapes. And then we combine this kind of like a primitive shapes into a more complex shapes. And then this complex shape get combined into something that we can relate into in our world. So that's the motivation for constructing CNN, okay? All right, so this guy, Jan LeCun, I guess that's how we pronounce his name. He is the father of CNN. So CNN it's actually been introduced, I guess the first study that relates the way that our brains work in visual cortex to the kind of like computer algorithm comes at, very, very old, 1980. But then it wasn't until 1998, so actually like almost 20 years later, that actually the CNN is being born. So it's quite a long time, right? And then this is actually quite old, right? Almost like 20, 30 years old in terms of machine learning. It's ancient already, right? So people have solved this for a long time, okay? So the way that the CNN works is that it mimics whatever I just told you, like the visual cortex. So first, we analyze, the input layer, which is the real image, right? But we don't want to analyze this like everything at the same time. We want to do local regions where we detect like primitive shapes first. And then we kind of build things up, along the layer to produce, like a more pattern recognitions on the complex shape on the higher layer, right? And that is where the convolution or the scanning comes in, okay? The way that we do is that we're gonna come up with something called kernel, okay? The kernel is like a receptive field in our eyes, in our visual cortex, right? So we see the image, but we don't see things at once. We're gonna scan through the image and look for certain patterns first. And that is how, like this operation is doing. Like these are convolution. And what convolution do is actually using the same kernel, it scans through the image and kind of detect some certain pattern that occur, like edges, like circle, like square, or something quite primitive, right? And this thing is gonna get mapped into the output layer. And the output layer is just a representation of that particular kind of pattern that the kernel is detected. And the kernel is actually something that we learn from training. It's not something that we have to specify. We don't have to specify what this kernel is doing. We just have to learn from the example what the kernel should be, from like all this loss function, okay? So the kernel is a 2D array of weights, the learned parameter, and the kernel scans through the layer with the convolution operation. Actually, it's called cross-correlation in other fields, okay? And then it produces the output, right? The output is actually just another two-dimensional data. We call it feature map, okay? Feature map, okay? You can think about feature map as the result from recognizing a different patterns, okay? That's analogous to our receptive field, all right? So for example, if you have an input like this, right, and you want to detect maybe the vertical edge, you can come up with a kernel that looks like this, which is 1 on the middle and the 0 everywhere else. Although in reality, we don't specify what the kernel is. We learn it, right? We have the network learn what the kernel should be. But if I were to give this kernel like this, and I scan through or convolute this one with the input, this is the feature map that comes out. As you can see that it kind of emphasizes the pattern that goes up, That's what the kernel is going to do, okay? If I want to detect something that lies along the horizontal direction, I would have the kernel that have 1 in the middle like this, right? And the 0 everywhere. And if I were to do the convolution operation with the input, this is my feature map. Because this one, as you can see, it emphasizes the feature that lies along the horizontal directions. But again, in reality, the feature that come, like the kernel, is going to be learned. So it's kind of hard to specify what each kernel does because it's all numerics, right? But I just want you to get the idea that each of the kernel is going to look for a particular things in the image, like edges, like circle, like curve, and things like that, okay? And that's gonna, that is going to help the network kind of constructing like feature, and then the feature can combine into another feature, and then in the end, it can help us do more classification of the image, okay? So why is this useful, right? I was telling you, like just previously that, the artificial neural network can do image processing pretty well, right? We learned that it can do handwriting with, like 95 or 99% accuracy. Like we tested that before previously. So why are we doing CNN, right? And the big thing about CNN is that it's reduced the number of parameters. It's the scalability issue, right? Our image that we did previously only have 28 by 28 pixel dimension. But again, for real pictures, it will be like 1,000. Like high dimension, like HD photo would be even more, like maybe like 4,000 pixels. So with ANN, obviously you can do everything that CNN do, but it will be overkill in terms of computational cost. So that's why CNN is a winner here, because you don't need a lot of parameter to do the same thing as ANN. So reduce parameter. And the key reason why CNN reduce the parameter is that you share the kernel. Like the kernel is actually a small matrix, right, that we need to learn. So these are the parameter, and it scans through the image. So then it means that we only need to come up with just a kernel, a small kernel, and it shares the weights all over the picture. We don't need to construct the whole kernel that is as large as the image. So kernel can be something that is like maybe 5 by 5, and then it can scan through the image no matter how large, okay? So essentially, the kernel can share, you can share the weights with multiple neurons in the layer, okay? So even if your image becomes larger, your CNN model actually stay the same in terms of the parameter, because you can have CNN that has the kernel of 5 by 5, and it can process the image that are 100 by 100 pixel or 1000 by 1000. It's still the same parameter model. So that's a big gain in terms of computational efficiency, okay? And again, I give you a simple example. If you have an image with 150 by 100 pixel, that's not really large at all, right? If you have a CNN layer with 200 feature maps, so that's its 200 filter, so 200 kernels, you only need about 50,000 parameters. So that's not a lot at all. But if you were to do this with the fully connected, so that is the ANN that we did previously, that would be about 600 or 700 million parameter. So you can see that huge gain, right, in terms of computational efficiency. So that's why CNN is actually the go-to architecture where you want to do image processing. And I mean, it's done everywhere nowadays. It's very common, okay? All right, and also the CNN is also translation invariant. So since due to the scanning nature of your kernel, like your feature doesn't have to be, it can be anywhere. Like your dog can be at the corner. Like if you have an image, right? Your dog can be here, or a person can be here, or the person can be here. It's actually make no difference to the model because of the scanning nature of the operation. So that's called translation invariant. So the model can recognize the location of your objects no matter where they are automatically due to the convolution operations. Okay, so that's also pretty nice, right? Okay, we're almost done, so stay with me, okay? So what we did previously, these are the grayscale image, right? When you have the grayscale image, you only have one matrix, right? But if you have the color image, that means that you start to have more than one matrices. For example, a color image will have 3 channels, right? So in a color image, actually in 1 pixel, there are 3 values correspond to the number, the intensity of the 3 colors. For example, red, green, and blue. So as you can imagine that even if you have like 28 by 28 images, right, you do have 3 copies of your data like this, red, green, and blue. It's called channel, okay? So you end up with the 3-dimensional array, okay? Even if you have 1 image, will become the 3-dimensional array because it has the width, right, the height, and the number of channel. So usually it's 3 channels for the image, the color image. Although some of the image will actually have 4 channels. It's called alpha, which is called transparency. But we're not going to talk about transparency in this course. But you can have more than 3 channels per se. So at least for color images, you need 3 kernels, okay, in order to take care of the 3 colors, even for just a single image. Okay, so 3 kernels now, okay, and each of the kernel will scan through the image like this. Okay, so the kernel is this the shadows in here, and then the output, and these are the output. Okay, so you do have 3 3 output per se for a color image. And again, what we do is actually if you have 3 output, so we want to combine them together. So you can simply just sum all the 3 values, the 3 matrices into the yellow matrix. Okay, so think about 3-dimensional input, right? And you have different kernel go through different channel, but then in the end, you're going to sum the output together in order to come up with just 1 layer like this. Okay? Although, okay, in reality, things are a little bit more complicated than that. Okay, so we don't need to have just, maybe in our 3D. So again, let me back off. So if we have 3 kernel that go through each layer, right, we can stack them up and call them filter. Okay, so that's the word filter. So we're going to call them filter from now on. Okay, so when we have different kernel operating on different channel, we stack them up in the depth dimension, and we call them channel. Okay, so the filter is actually a 3D array now. So the input is 3-dimensional array. The kernel of the filter is also a 3-dimensional array. Okay, so the picture that you want to visualize is something like this, right? So these are the input image. It is, width and height, right? But then it also has the channel dimension. So for the simple color image, you would have 3 channels. So this one would have like a 3-dimension in depth direction. Okay, and then the filter would actually be a little bit a smaller size, right, in terms of the width and height dimension, but it should have the same depth or the same number of channels. So this one will be 3 for the image, for the input image with the 3 channel. Okay, and once you do the operation, which is the convolution, you should end up with just a layer like this. Okay, so that's how you should visualize the operation in the CNN. Okay, so a block with 3-dimensional, like a block like this, with the filter that is also a block in 3 dimensions, but end up with just 1 layer. That's for 1 set of filter. Okay. A little bit more is that actually we don't only have the filter we also have the bias. So the bias is just a constant that you add to the output, just to shift things around, almost like a y-intercept value. So in addition to the filter, you're going to have what's we call the bias. So the bias is just a scalar value, okay? Again, if you have one filter, you get one layer, okay? And that's called feature maps, right? But you don't have to have one filter. You can have multiple filter, which we always do actually. So we don't have one filter. One filter only detect one type of pattern, but we want to detect multiple type of patterns. That's why we're gonna have multiple filter, okay? So it's kind of complicated in a way that filter is just recognizing one pattern. If you want to do multiple patterns, we do multiple filter. Since each filter will give you one layer, right? Multiple filter will give you multiple layer. As you can imagine that I extend the green layer, right, just for one single layer from one filter, so one orange block, into the three-dimensional version of the green block because it comes from different orange blocks, okay? Each of the orange blocks contribute to just single layer of this, all right? So the second filter will give me the second layer of that block, and the third filter will give me the third layer of that block, okay? So that's how we're doing it. So actually, if you think about it, the filter is actually four-dimensional matrix. It's actually four-dimensional tensor now. It's actually not three-dimensional because you can have multiple filter, okay? Right? And also you can have biases per filter. So you do have, biases too, multiple biases. Each biases will contribute to each of the layer in here, okay? Okay? So that's what it is. So it's going to be four-dimensional array for the filter. It's going to be the width and height. That is the scanning part, right? And then the dimension of the input, which is like let's say you have the color image. It's going to be 3 channel. But then the output, you can have multiple filter. So it's usually a lot, actually, in the real calculations, okay? And then you also have the biases, which is equal to the number of the layer of the output layer. Okay, so that's the whole picture that I guess if you can visualize them, things will get more clear when you start to construct such network in TensorFlow. So the input is going to be the three-dimensional layer, right? But then the filter is going to be, like there will be a bunch of filter that gets operating on your input layer. One block of this is one filter. So you can have multiple filter. Each of the block of filter gives you one layer in the output layer in here. So if you have multiple filter, it will be equal to number of layer in your output layer. And we call it feature maps. Okay, so this one we have multiple feature maps because we have multiple filter that operates on your input layer, okay? But that's not the end, right? These are the hidden layer, right? But we can even have even more filter that operates on the second layer. So these are the filter that gets operate on this layer in order to produce a single layer on the next hidden layer. And another filter here that get operated and then produce another map on this layer. And it can go on and on and on and on. And as you can see, this allows us to construct, like something that I was telling you, like the primitive pattern recognition. And then maybe this feature map in this layer detect edges, circle, like a sharp corners. But then when you do another filter on this one, this feature map start to combine features together to get a more complex shape. And we can have more feature, more layers in here, and it keeps going on and on and on until we get into the place where, like actual pattern or actual shape or actual objects is being recognized. And that is essentially motivated by the visual cortex, how the visual cortex kind of works in our brain. Okay. All right, so let's do some of the exercise before we go through the examples. Okay, so let's say we have the image of 32 by 32, right? And then it's a color image. Okay, so that means that we're going to have 3 channels. Okay, so 3 layers of 32 by 32 matrices. Okay, and we want to recognize multiple patterns, right? So we want to recognize 32 patterns. So we choose the number of filters to be 32. Okay, but each filter doesn't have to be large. It can be as small as 5 by 5 because like the pattern that we are recognizing usually happen in a local region. So you don't need a large filter, and that's actually why CNN is quite efficient in terms of computation. Okay, so we use 5 by 5 filter that scan through the image, but then we need 32 of them because we want to recognize multiple patterns. Okay, and the padding is called valid because we don't pad at all. Okay, the output shape is going to be smaller. Stride of 1 and 1 meaning that when we do the scanning of the kernel, we don't skip any blocks at all. We're scanning just like step by step. Okay, so how many parameters do we have, and what is the output size of our feature maps? Let's work it out. Okay, just for the just to make sure that you kind of get familiar with the number and all the terms, right? I'm not going to test you in this in the finals. Don't worry. Okay. So first of all, we have the input image that is 32 by 32. We have 3 of them because it's 3 channels. Okay, and we have filter. We want to recognize pattern. So filter is going to be 32 filter. So, but in each filter, remember that each filter will become a 3-dimensional matrices too, because each 5 by 5 layer got operating on each of the channel. So you need 3 of them per filter. Each filter consists of 3 layers of 5 by 5 matrices. Okay, but we need 32 of them because we want to detect 32 patterns. So think about this. We have 32 sets of that 3 layers of 5 by 5 matrices. Okay, so how many parameters do we have as of now, right? So think about this. Each of the filter is 5 by 5, right? And then there are 3 of them. So 5 by 5 multiplied by 3, right? But we also need biases, right? So we plus 1. And we need 32 of them. So that calculates to be 2,432 parameters. Okay. Again, the output size, what about the output size? So again, this one I would say that it's very, very small compared to if you want to do 32 by 32 images with ANN, your parameter will blow up pretty easily. If I were to recall correctly, we did something before with ANN with the MNIST data set, and I think our parameter goes up to like 10,000 already, like 100,000 already, right? This one is in the order of 1,000. So it's essentially, you can see that apparently it's much smaller, right? But what about the output size, right? The output size can be calculated using the same equation that we used before that I worked it out. So this one, like you input the number of the input size, padding, stride, and then I don't remember the equation, but if you work it out, it will become 28, say, per dimension. So that means that my input side, my output side will be 28 by 28. So that's something to keep in mind, that once, like depending on your padding and stride, then your output feature map can become smaller or even larger if you set it in a certain way. Okay. All right. Again, just to make sure that I got everything correctly, like in the I guess in the real calculations, we don't just input one image, right? This is just one image. But in reality, we are inputting multiple images. Like when we train, we gotta do batch of images. So that means that actually when we do our real calculation, we are inputting, like our training data will actually consisting of batches of images. So each of the blue block is actually one image. So we do batches of images. So it's going to be 4-dimensional data anyway. Okay. I know that's a lot to take into, and it's okay if you don't get all of them, but I just want you to get familiar with the term so that when we go through the example, you know, some of the words ring the bells to some extent. Okay. Okay, so we are done with something called convolutional layer. So convolutional layer is essentially the kernel that do the convolution operation to the input data, right? But in the CNN, the real architecture, actually there are more, because just the convolutional layer itself is actually not enough to do for the computational efficiency. There is another trick that we can do. It's called the pooling layer. Okay, so the pooling layer is something that it's called it aggregates the input so that it's kind of making sure that some of the feature gets enhanced. For example, the max or the mean. So the pooling layer has nothing to learn, but what it's doing is actually look at the image and extract certain features that we want. For example, the max feature and the mean feature. And this one also has a size, stride, and padding type, similar to the CNN layer. And the most common padding layer, pooling layer that we want is actually max pooling. So this one is just going to collect whatever the max layer, the max value in that certain aggregating region. Okay. For example, if I have like an image like this, and if I want to do the pooling layer of 3 by 3, so that means that I'm going to look into the little patch of 3 by 3 in my input, and then extract just the largest layer from it. So 8 going to the output like this, okay? And then I move to another scanning region and extract the maximum value like this. And also if I look at here, it's going to be 6 and 3, right? So as you can see that this pooling layer, one of the things that it's doing is, depending on the size of the output, it's going to kind of like detecting whatever the most important from that particular region. For example, the maximum value is usually the important information that you want, but you want to disregard the rest because it's noisy. So the max pooling is kind of nice in terms of kind of cleaning the data, like get rid of all of the noise and give me, you know, the most important thing so that I can detect more pattern easier, something like that. Okay, so the advantage of pooling layer is actually reducing the computational expense, because if you make it, if you end up with a smaller size, you can always you know, increase your computational efficiency. And also it has something called local invariance, meaning that if you have small variation in your image, the max pooling is always going to result in the same thing, which is always going to be the maximum value. So slightly change in your image won't be affected by the max pooling. So it's kind of nice in terms of giving your model more robustness per se. Okay. Another thing that people usually do is called dropout layer. So dropout layer is just helping making the training data a little bit more challenging for the model to learn. So the dropout layer is essentially dropping the connection between layers, so that the network is forced to learn, you know, the new ways of connecting between the layer. Okay, so that's another way that helps the network kind of finding different ways of changing the weights, basically. So during the evaluation, we don't use the dropout because that makes our network worse. But during the training, some people do dropout layer. Okay, so as you will see that I also use it too. Okay, and also the loss function is something similar to what we did with the classification of the artificial neural network. So we are using something called sparse categorical cross entropy. So this one right here, we're using this guy. Okay, just to mention it, we are using the same thing because we always want to do you know, like the classification with image, right? So that with the loss function, okay? So if you want to construct the convolutional model, then this is something that you would typically do. So input data is the image with multiple layer for the color images, and you pass it to the convolution. So the convolution is a layer that contains the filter, and then it's producing the feature maps. Okay, and sometimes you might do pooling, because pooling will help make things smaller, and then it helps you with computational efficiency. And you might want to do another convolution. Usually people do convolution with greater depth. So the deeper the layer, the more depth or the more feature maps that you would include. And you keep do pooling, and then the convolution and pooling until you end up with a very, very small size feature map, but then very deep, okay? And later on, you're going to do flatten. So this is the flatten. Flatten meaning that whatever you get in terms of like a three-dimensional matrices, just make it into just one vector. And then you do the fully connected. So this part is actually just A and N. But again, the A and N only happen toward the end. So that this part, even though it's going to be, you know, like it's going to give you a lot of parameter, it's going to be cheaper comparing if the whole thing become A and N. So that's what the CNN will come and help during the training in this part. Okay. Okay. So why don't we take a smaller break and then come back for the just a smaller, a quick overview of the actual architecture, like a actual example. Schedule hand wet, okay? All right, see you soon.